Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure to welcome Victor Brabermann from University of Buenos Aires. Victor is, among many other things, he is doing advisor of two of our MSR fellowship LATEM program students. And Victor will talk about model checking, scenarios, and slicing in application to real-time system. I find this very interesting because real-time is something we are not looking so often here at Microsoft Research, and I'm looking ahead to your talk, Victor. Thanks for being here.
Thank you, Wolfgang. Well, first of all, good morning. Well, as Wolfgang said, I will be talking about somehow a cohesive tale of a set of tools we've been developing in this domain, which is the analysis of real-time systems. Well, this is work of many people from Universidad of Buenos Aires and Universidad de la Empresa. So let's go directly to the topic. We're talking about real-time event-driven applications. This domain is characterized by the criticality and this sentence that I wrote here, which is confidence is really difficult to achieve with traditional methods like testing. Okay, so there are many work to try to solve this problem from more modern verification technologies like model checking. Okay, model checking especially has some success stories on some kind of applications, especially, for example, API usage or the verification of protocols. Okay, so it's natural to think whether model checking can help us to verify this kind of systems. Still, we will see in this presentation we have some scalability and usability challenges to solve here in this domain, and that's mainly the topic of the talk, and we show how we try to solve some of these problems. So I just said model checking just to be sure that we have a minimal background on this. Let's say the model checking is it's a name for a family of algorithms that try to solve verification problems in a highly automatic fashion. So algorithmic way to check properties over programs or models. And we actually will work on model checkings, models of real-time systems. Actually, we will take a look at time model checkers, where the models are written to take into account timing constraints about the system. So the models are not just about states and events, it's also, they talk about timing constraints. Okay, so that's the kind of models we would like to check. And they will be particularly based on timing automata, which is one of the most popular formalism to express real-time systems. Okay, there are a lot of model checkers. Probably the most well-known ones are UPAL from Uppsala and Aalborg universities, and Kronos from Verimac laboratory at France. So let me give a brief idea what timing automata is. Timing automata is basically a finite state machine where we have states, transitions, but we also have timing constraints in the form of, we have this notion of clocks. Okay? So we reset clocks and we put constraints on timing using those clocks. We essentially can say things like, well, there is a deadline, I cannot stay in this location for more than 30 time units, then I can leave this state, we call it location, if the time elapsed is greater than 3 time units, then I reset this clock. So this is the flavor of the things that we are modeling using timed automata. Okay, so it's like a finite state machine with clocks and Boolean combination to write guards and to write, this is a guard, and to write invariant. In this case, this is an invariant associated to a location. An invariant tells us in general, the maximum amount of time that we can spend at a given location. Okay? Yes?
So, I'm sorry, could you explain the guard x greater than 3 again?
This means
at least 3 time units since we came into the state that's the source of the edge, or?
It's 3 time units since this clock was reset. So, well, example is not complete. We don't know if that clock was reset earlier, but in this case, well, if we have here x is reset, and if we had here a transition with a guard like this, it would mean exactly what you said, is I can leave this state if 3 time units has elapsed since I arrived to it. Okay, but in this case, it's not clear because, well, if this is the initial state, yes, that's true because all clocks are reset when initialized. The semantics is given as a label transition system. This is not unusual in formalism about behaviors. What is particularly interesting is that states are infinite. You have a location, and you have clock valuation on real numbers. Okay, so states means where are you in the control location, and which are the values of clocks. Okay, as you can imagine. The model checking is done using some sort of symbolic representation of states, okay? Because you have an infinite number of states, so we need some symbolic representation of states. So model checkers are based somehow on a symbolic representation of a state space, and fortunately, things like reachability are decidable in this formalism, and also checking quite rich temporal logic formulas, okay, like TCTL. So that's the thing that you need to know about time automata. If you have any other question, please ask me, okay?
So this angel brace is the time interval, which is in the transitions you have noted there, 4,4 or 0
well,
is the time interval? Or?
No, this is actually a clock valuation. This means
for different clocks, for 2 clocks.
Yeah, for 2 clocks, for X and Z in this case. Yes, let me show you this. This means I'm in 0 location, it's an ID, with the clocks X and Z evaluated to 4 and 4. And then after taking this transition, okay, which is labeled by the event A, then arrive to 1, the location which is called 1. And here you see X is 0 because it was reset here. Okay? But this is instantaneous. Set clock hasn't changed. Okay?
It's a subscript on the transition is the time taken for this transition.
Yeah, yeah. And actually, this is a time transition. We have 2 kinds of transitions in semantics. Discrete instantaneous jump, which means jumping in the graph, and time-elapsing transitions, which means I remain in a given location, but I let the time elapse. So in this case, I'm, for example, here in location 1, okay, with valuation 0 and 3.1 for Z, okay, 0 for X. And this transition, which are an infinite number of this kind of transition, means, well, let's elapse time 1.5 time units. That would yield the following state. 1, because I can't change location, and 1.5 added to both values, because the rate is the same for every clock. There are more sophisticated models where time is not required to grow at the same rate in every clock. Okay? But in this case, we're just adding this value to the clock valuation. Is that okay?
Yeah.
Well, this is in a nutshell what time automata is. there are tools to check things like reachability and other time logics. Okay, so give me this is what VinTime, our tool set, is about. Our tool is about trying to solve some usability and scalability problems when model checking real-time systems. Okay, so we have mainly 4 fronts. One is a compiler for design level description of the system into time and automata. Okay. We'll see, we'll use scheduling theory to do this kind of translation. We have a property language based on scenario notation to write properties about the time system we want to check. We have optimizing technology to do some property preserving model reduction, okay, so to make it things easier for the model checker. And we also have developed a distributed model checker. But in this case, we actually could plug any of the available model checkers in our tools, like UPAL, okay? But this is something that was also done in this project. So let's give some names to these pieces. We have Lapsus, which is the translator somehow from real-time system designs into time and automata. We have BTS, which is a notation for writing properties, for writing real-time properties. Okay. We have OpSlice, which is the optimizer, which is mainly devoted to reduce the time and automata model to make things easier for the model checker. And finally, we have Zeus, which is our distributed model checker, but this can be changed by any other time and automata model checker. So this is a more accurate architectural description. We have Lapsus model generator. Okay. We have VTS editor, let's say Tableau generator, because actually what we draw here, the properties are translated also into time and automata. We'll see that later. So these are the inputs for the optimizing technology, the optimizer called OpSlice. Okay. Well, they share some information like in the event alphabet because we have to bind properties to the design itself. And then once we have the optimized model, we feed it into some model checker, in this case Zeus, but this could be replaced by any other model checker. Okay, and then we have the typical cycle with a counterexample and things like that. Okay, I won't spend too much time about that part of the story. So let's see a little bit about what has been done in terms of model checking real-time system designs. When we look at the tools for model checking real-time system designs, what we found is, well, they claim to work with general application models. That means if you look at what the traditional community of real-time system design analysis had been doing, they usually constrain the application model. They say, well, this application model is like as follows. You have periodic tasks, sporadic tasks. Okay, we have a fixed priority scheduler and some set of constraints on the way you can build application. Okay, and then they develop analytical tools to calculate worst case execution times to know whether task will satisfy deadlines. Okay, that's more or less the way classical approaches to the analysis of real-time system have been doing. When you look at model checking people, they claim, and they are usually right, they have more general application models because they play combinatorially with the application. Okay, as model checker can do. They can be more precise than analytical tools as well, okay? The way they calculate is actually by running the model, okay? Symbolically, but running the model. They also have more general query languages. They can express complex properties about the system, okay? Like end-to-end properties or things even more complicated, involving several components and connectors, okay? That's the good news. But the bad news are that usually, well, there's a usability problem. Expressing properties is usually hard, okay? And there's another problem that I will spend a little bit of time on it. Scalability is still a big issue. And what do I mean by scalability in this context? Suppose you have a design with 100 of threads, okay? So you have a big design of a system, 100 of threads, and you want to analyze a property that actually, if you look at it functionally, it involves just a few threads, okay? Because it has to do with a scenario where only a few threads are involved, okay? An end-to-end property about a subsystem. The problem is that in model checking, the first thing you will try to do is it is called some kind of property-based localization. That means if you have a model and you have a property, and property is talking about a submodel, you will try to check the property of a submodel. Model checking is very expensive. Technology should, the smaller the model, the better, okay? So this is also known as cone of influence or model slicing, and that thing doesn't work with traditional models of real-time system. Okay, why? Because if you think about modeling real-time system, what you more or less straightforwardly will do is to model the scheduler. Scheduler is another component that gives control to the different threads, okay? That scheduler actually imposes a strong behavioral coupling, okay? So although you have threads that functionally had nothing to do with a property, they have to be considered when model checking because they influence timing behavior of the other threads, okay? So that's a problem. You have higher priority threads, for example, that may interrupt the threads that you are interested on. So you have to consider those threads when model checking a property that could be, like here it says, be involving intuitively just a few threads. Okay? So this is a problem. I cannot localize the property. So what we've been doing with Lapsus is actually changing the way of thinking or the way of using model checking in the context of real-time system design. We said, okay, it's not really a bad idea to have a constraint application model. I mean, these people aren't wrong. I mean, they're imposing architectural style to make it easier to analyze the applications that are developed using that architectural style, okay? So that's not a bad idea. So if we fix the application model such that we have a way, analytical way to calculate worst case execution time, yes, then we will use model checking for checking properties that cannot be easily checked using analytical tools. So we are like enhancing the analysis capability of these kind of tools using model checking. Properties involving several components, as I said previously about model checking. So I would like to prove things about freshness, bounded response, correlation on an application model that allows me to calculate worst case execution time of a sequence of code. I don't know if it's clear enough, but there is a jump between having a way to calculate worst case execution times of threads and analyzing a property involving several threads, okay? And that's the thing that we are doing with Lapsus. Yes?
So how non-deterministic is the scheduler?
How?
Non-deterministic. So when the scheduler says, I want to interrupt this high priority task after 10 times, 10 milliseconds or something.
Mm-hmm.
So does it guarantee exactly after 10 milliseconds?
Well,
Or is there a range? I mean, so how do you model these kind of non-determinism? How do you model the time slice in the scheduler?
let me give you a couple of answers. In the context of Lapsus, our tool, we're working with fixed priority scheduler. Fixed priority scheduler is not, at least at a given level of abstraction, is deterministic. So if there is a thread that should be, or process that should be launched and has higher priority than the process that is currently running, it should preempt the process that is running and put the highest priority process on the processor, okay? Well, in general, you could have some kind of scheduler with, I don't know, non-deterministic bounds or intervals. That is not the thing that we are trying to solve, okay? And I guess that other techniques, like the ones I mentioned, like times, well, they have the ability to specify with a timer automata that the task should be launched between, I don't know, 5 and 10 milliseconds after a given event. So it is possible to do that, not in our context where the scheduler is traditional fixed priority scheduler with analytical tools underneath. Okay?
The time values for your timed automata model.
How?
I mean, where do you get the time values? I mean, where does the time come in your model? So if the scheduler is fixed priority,
yeah,
and so when you're timed automata, you'll have these
we have
clocks, right?
Yes, I don't know if we will answer the question you're posing, but you have periodic and sporadic tasks, and periodic, the period has to do with the time of interruption. Sporadic task means that usually tasks attending some external interruption, and sporadic means that we have a minimal interval time. Okay, this has to do with the way it is calculated, the worst case execution time. I will come back to this later. So these models will be suited for property localization. So that's the thing that we would like to achieve is, well, once I build these models and I have to check some property, I have a good way to localize which is the part of the model I should take into account when model checking. Okay, is that clear? So this is kind of system that we would like to analyze. In this case, we have a distributed system with a central processor. Okay, so the system is deployed in 3 processing nodes. Okay, in one processing node, you have something that we call a requester. Okay, that broadcasts a signal. This is a kind of connector, broadcast connector. Okay. So you have another sporadic task attending that interruption that, well, when waking up, it reads from a shared variable some information that was actually periodically written by a sampler in this node. Once that information, the last sample value is read, it is sent back through other connectors to a sporadic thread that runs here in this central node that actually takes both answers and merges, correlated. Okay, it's like something that sends a signal, it broadcasts the signal. These 2 nodes do something, okay, with that signal, and they answer back, and that information is again correlated here. So this is more or less the kind of model we're trying to analyze, okay? And we will see later how properties like freshness, correlation can be written on this kind of models, okay? Do you have a question? Well, actually this model, for example, is composed of 12-time automaton using Lapsus approach. We will see how Lapsus works in a few minutes. So the application model is the following. We have event, sporadic, and time trigger tasks, threads. I mean, we are not being very specific about this. Distributed in a set of processors, as we see. We have non-blocking connectors. The idea of non-blocking is technical, but has to do with the way we can calculate worst-case execution time. If connectors are blocking, the analytical tool is much more difficult to specify. I mean, it's a harder work. We have preemptive fixed priority scheduler. Okay, this is similar to rate monotonic analysis application models, if you ever heard about that kind of stuff. So we have three types of, and we can express the behavior of tasks, okay, of each thread, and we can also express the behavior of the environment. Okay, so we have some capability of describing the behavior. So we have three elements: the architecture, task behavior, and the environment and connector behavior. So that's all these three things made up the model that we want to analyze. Okay. So, which is the idea here underlying lapsus? Well, it's based on the following statement: scaling discipline is a way to achieve fair and predictive computation. Okay. So, what we do is we use the worst-case completion time calculus, which is provided by the analytical tools underlying the application model that we fixed, okay, to build conservative models based on timing automata. In that way, we are not modeling the scheduler. Each task is a timer automaton, and the timing, I will see you later, but the timing effect of threads are somehow calculated on using the worst-case completion time calculus. Okay? And these models, the rationale here is to build simple models amenable to local analysis, as I was telling you before. Well, actually, these models are not directly built on top of timing automata. They are built on a given notation that is in turn built on timing automata, which is input-output timing components. That adds some controllability information about these events and the way the timing automata are synchronized. But this is a rather technical issue. I won't spend time on it unless you ask me later. So the idea is the following. Suppose you have the specification of the behavior of a given task. Okay? Here what we see has to do with timing information. Okay? This is one, in this example, means the activities done on this node take one time unit of computation if they were run in isolation. Okay? This is the worst case execution time of portions of the code when we are running them without any interruption. Okay? This is typically what people from real-time scheduling theory have as an input. Okay? They know how much time would the task take to run in isolation. Okay? Then, so for example, here what I know is that this is a sequence actually of actions, but what I can say here is this will take between 48 and 53 time units without any interruption. Okay? We use the worst case execution time, the worst case completion time calculus to get the values, okay, the actual deadlines for this portion of code. That is, we take into account all the tasks that may interrupt this task to calculate the worst case execution completion time of this portion of code. Okay, so there is a kind of transformation from this actually 53 into, in this case, 57 time units. Okay, that has to do with the amount of time that was somehow steal by other threads while running. Okay, and that is calculated using the worst case completion time analytical tools that we have in the underlying application model. Okay. Well, we add some information that has to do with the periodicity of the thread. Okay, this 110 time unit here is here because, well, it's not written here, but this task is periodic with a period of 110 time units. Okay, so somehow we build a time automaton. Okay, from these activity diagrams. Okay. And then, so we use this worst case completion time to achieve that thing. And we don't need to model the scheduler, okay? And that make it easier to, as we say later, localize the property. Now, let's come back to the properties we would like to analyze. For example, here we have the following properties. Answers to the requester, okay? Reach the correlator in less than 190 milliseconds. Okay, that's a kind of property I would like to prove. Other is data collected by the correlator here, okay, is no more than 135 milliseconds old. Okay, this is a freshness property of the system. The other property that I might like to prove is that correlated data, because here was sampled no more than 153 milliseconds apart, because you have samplers here, they write things, and we want to be sure that things weren't sampled too far away, okay? So that's the kind of examples, property we would like to do to prove. These are heavily based on event flow, okay, of the system. So typically in a model checking community, what you do to try to prove that kind of properties is to write some kind of automata observer of the system, okay? That observer watchdogs the system, if the system has a problem, okay? If the system violates a property, the system leads the observer towards a given location, okay? So the question is, can the system together with the observer evolve to a given location? Okay, and that, if I can answer that question, I will know whether the system has a violating behavior. Okay, that's more or less clear. This is this observer automaton, and we can do it. I mean, we can check that using model checking tools. Okay, that kind of properties is the one that we can check using the model checking tools. So, but I mean, writing an observer, it's error prone. It's a very heavy task. So we develop BTS, which is a visual time scenario, which is a notation for writing event-based or event-intensive properties, okay, like the ones I mentioned. It is based on a very intuitive graphical syntax, which has draw points and arrows. Points meaning events, arrows meaning precedence, usually. And we can also express timing constraints between events that we draw, okay? So we have a formal descriptive semantics of this, a very simple semantics based on matching on traces. And we provide a way to translate those scenarios into timing automata and then use model checking tools to prove whether those properties actually hold or not, okay? So let me go directly to a very simple example of what I'm saying. Suppose that I want to express the following property. Something like there is a stimulus E followed by two responses, R1 and R2. These are labels, okay, which are not separated by another response, R3, okay? This is written, actually, we have a lot of shorthands for writing this, but I mean, in our kernel notation will be written like this. We draw this scenario, okay, where we have a point for E, okay, for the stimulus E. We have two other points, one for R1, the other for R2, okay. both have this this arrow that means precedence, okay? Means E should occur before R1 and R2, okay? And we have these labels on arrows, on top of arrows, or on top of this kind of constraint, which should be read as this shouldn't happen in between, okay? This actually, well, we don't have the negation symbol, but this would be like saying, okay, you should match an E, you should match R1 and R2, both be after the E, okay? In between, there is no other R1 for the case of response 1, no other R2 in case of response 2, which actually means this is the first R1, this is the first R2 after the E, and in between, R3 does not occur, okay? And let's see it, let's take a trace, okay, of events, very simple trace, just labels, okay? And let's try to see whether we have a match here. Suppose I try to match here this as stimulus, this as response 1, and this as response 2. Well, this is not a match because you have R3 here in between, okay? Now let's try another match of the same trace. Okay, let's take R1 and this R2 instead of, oh, this is a different trace, but don't care. But this is a match because there is no R3 in between and the precedents are satisfied. Okay? And this is also and shows that without putting any precedence between these 2 points, so response 1 and response 2, we allow both interleavings. Okay? And when we come to event, we can put also in on top of arrows or constraints, timing constraints, okay? So we can also specify things like, well, these 2 responses come not in this interval, timing interval, okay? So when we check a match, we add a timing constraint, okay? So in this case, for example, the distance is 76, and 76 is in this interval, so this is not a match, okay? Well, in this case, the answer is yes, because the distance between R1 and R2 is 5, and 5 is not into that interval as specified, as required by the scenario, okay? Well, don't matter. We can do the same. So what have been done is actually the definition of a language and a description.
So this RTS notation, does it have any predecessors, or is that the parallel notations which exist, which try to, I mean, it looks to me very original somehow.
Well,
kind of thing, or is there some?
There are some similarities. We can talk about them later, but trying to think which is the closest work on this. Probably we can compare it a little bit with some trigger notation. We will see it later. But yes, there are some features that are novel in this notation. Okay.
I thought there might be. If you look at the UML notations, then you always have some tradition where they come from pencil and paper, kind of writing systems. So maybe in the real time community there was also something like this which inspired RTS. That was my question.
Well, we were not aware of something really, really close to it. I mean, there are, if we take any of the different related work, we found several differences with them, like light sequence chart, UML sequence charts, or triggered message sequence. Okay, I can talk about them, I think, later, because I need to update all the previous work to make the comparison online. Okay, so for sure, most of something that I can say about this is that most of previous work, the semantics was given directly building an observer automata. which is something that something would like to have to check them. Okay, so if you look at previous work on specifying system using scenarios, usually they give semantics directly translating them into automata. So they say, well, the semantics of this graphic is actually apply this algorithm, you will get an automaton, and that will be the semantics. And we try to give more declarative semantics, like, well, what does it mean for a trace to match this scenario, okay? And then we provide an algorithm way to translate it into an observed timing automata. It's like, well, one thing is to give a clear semantic, and the other thing is to have a way to check it, okay, a way to check it. Yes, Nicholas?
Yeah, I think Wolfgang's question aims not that much as the contribution of BTS, but more to its intuition, let's say. So that he's asking, is this point and arrow notation derived from some other notation that people can relate to when they see some of these diagrams so that it's natural for them? Or is it just a completely new notation that people have to get used to it? Am I right? Or, no? Okay.
Okay, but it's another question.
Okay.
Well, it's, in some sense, it's related to timing diagrams. In that sense. But, yes.
Okay.
Should I go on? Okay. So we translate BTAs into timing automata. Details are not shown here. And then we compose the system and the analysis, the design, with the observer that we obtain with this translation. Okay? And we check, essentially we check reachability. Okay? Using tools like Chronos and UPAL. Okay? That's how it works. So this is an example of the remote sensing that I've shown. This has to do with the correlation property. Actually, what I'm doing here is writing a pattern that would violate the correlation property. Without going into detail, what we show here, this is a set of, this is a sequence of events that occurs, okay? That both sequence of events are concurrent, they are not necessarily related, okay? And both actually are merged into very same event. That means that these two events, these two sampling events, actually sample information that will be correlated by the system, okay? This is more or less what this notation says. The sampling itself is complex to express the property because it's really related to the way that information flows into the system. So what I'm saying here is, okay, it would be a problem if two samples that were taking more than the deadline I specify are actually correlated by the system, okay? And so if I try to write this by hand, it will be practically impossible because the observer that we obtain using the tool has this size 38 nodes, okay? It's a graph of 38 nodes, and more than 400 transitions, okay? Well, we can argue that this is probably not the minimal way, but probably it would be more or less of that size, okay? Well, and we model check it. We actually found a bug. In this case, it's an old value. We did it again in less time, but in this case took 10 hours. Okay, that's the kind of things that we would like to, and we are doing with BTS over the real-time system designs. Okay, and there's something more about scenarios, which is the BTS scenarios, as shown till now, are somehow existential queries on traces. Okay, that means we are asking whether this pattern can be matched in a trace of the system. Okay, that's what I'm trying to find out. But in general, people think different about properties of the system. They don't think on a negative way. This is a negative way of thinking of the system. I write down a pattern that means, well, the property is violated. Okay? People usually think more in a positive way, like, well, if something happens, some other event should happen eventually. Okay? So we develop what we call conditional scenarios based on BTS, and actually we will see it later. The verification of this kind of scenarios will boil down into the verification of BTS properties. Let's see this simple example. Suppose you have an access request, okay, event, an access granted event, okay? And this is, when I wrote this arrow in this direction, means it's a shorthand to say this is the previous access request of this access granted, okay? So, and log off here says there's an access granted, okay? This is the previous access request, and there were no log off in between, okay? So now I want to express that if I see this situation, if I match this pattern, then there's a couple of things that should happen if I see this. Actually, what I want to express is that the password has confirmed either in between, okay? So if I get access after request, either I get a password confirmed in between, okay? Or the password, in the numbers here means we have two possible consequences, okay? Or in the past, the password was confirmed in the past, and and there were no timeout, okay? So it is like saying, okay, either in the middle I ask for the password, or the password was confirmed in the past, but not too far away, okay? This is less than a given timeout, okay? So it's saying this is the antecedent. This is like A implies either B or C, okay? Which is B in this case is, well, if A happens, either B, this is a given situation where the password was confirmed in the middle, okay? Or C, in this case, we're talking about the password confirmed in the past, okay, without a log off, and not too far away, okay, in the temporal distance. Okay. 7 minutes. Okay, let's go further. Well, I won't explain this in detail, but the way we check this is by building a set of negative scenarios standing for ways that this conditional scenario might be violated. Okay? And this is done automatically through a set of rules. For instance, there we have BTS scenarios that stand for the violation of this case, the case 1. In this case, we see, for example, that a violation would be, well, the antecedent here, but, for example, no password confirmed. Because here I'm saying the password is confirmed in the middle. Here we see that there is a password confirmed, but the password was confirmed before the access request. Because here I'm asking that the password confirmed is done after the access request. Okay? So here are the negative scenarios just for the first case. Okay? And we have the set of negative scenarios for the second case. And what we do is we fashion the negative scenarios of the first case and the second case to get this as the final negative scenarios. These are the cases that would violate the property. Okay? Let's take a look at one of them. For instance, in this case, we are saying, well, the password is not confirmed in the middle. Actually, it's before the access request. And the previous password confirmed, which is actually these 2 points should match to the same event in the trace. Yes, there is a password confirmed, but it exceeded the timeout. Okay? That would be a negative case for the general situation. Okay. The other case is, well, the password is not confirmed in the middle, is confirmed in the past, but there is a logoff in the middle. Okay. And the other case has to do with, well, no password is confirmed. Never was confirmed a password since the beginning of the system. Okay? And this is automatically obtained by this process of generating negative scenarios. Okay? The process also generates some inconsistent functions that statically we can discover that they can happen actually in the system. Okay? It's not necessarily to model check. So the original problem of checking conditional scenarios, it boils down in checking, in this case, these 3 negative BTS scenarios, the ground scenarios without conditionals. Okay? So this is like negating the conditional. Okay, let me give you a fast introduction to Upslice. The problem is, well, we have the model, okay? We have this property I want to check. This is, for example, comes from BTS translating into automaton. We try to check whether the system and the observer together can lead the behavior to a given acceptance state, okay? So we're trying to check this kind of property. And what we do with Upslice is actually discover at each position of the observer which is the relevant part of the system that should be analyzed, okay? This is a localization tool that actually works at the observer location level, okay? Okay, when I'm here analyzing the influence that the different components can do between them, can perform between them, I discover using static analysis which component of the system should be actually tracked while model checking. Okay, so I'm reducing, in general, the number of components I require. I ignore components once I progressing in the observer, okay? And this is automatically done, so the model is instrumented once one knows which components are relevant in each location. The model is instrumented in such a way that we ignore this part of the state when we advance on the observer. In that way, we achieve really some dramatic speed-ups in the checking. Okay, so we get an equivalent and optimized model. It's equivalent in terms of the properties that we would like to prove. It works particularly well for these decoupled models that we built for Lapsus. This is the way, I mean, this where things are fit together. We generate from BTS scenarios observers. We use this optimizing technology on models to discover which are the relevant components. And this works really good for the decoupled models that we are building using Lapsus. Okay? We don't have the scheduler. If we have the scheduler, everything will be relevant, okay? No matter where I'm in the observer, okay? So this is what we do. We transform the network of automata into something which is bisimilar somehow, which means we are preserving logical properties of the system, okay? Well, don't worry. These are typical tables showing a dramatic speed up in this case, which is quite expectable because you can expect that because, I mean, the model checker is really sensitive to this kind of state space reduction, okay? So this is, again, the architecture. And these are some future work. Well, Lapsus itself, it would be interesting to have support of other application models, okay? So one of the good things of Lapsus is also the weakest part of Lapsus. We're fixing an application model so we can take advantage of worst case execution time calculus. So if you like to deal with other architectural description languages, other application models, we have to figure out how to calculate or check the community of real-time system design analysis, how they propose analytical tools for those kind of application models. Okay. In terms of BTS, well, we look in at some compositional operator, scenario control, filtering of behavior, triggering notation, event correlation. There are many things around this notation that might go in the future. We are working especially on something that we found particularly interesting is if we take scenarios written in BTS and we manipulate them somehow, if we add detail, we get better performance of the optimizing technology. And we can check whether that specialization of scenarios is the right way to do it. We can talk about this later. Well, and CUs, I haven't talked about CUs, but working on having forward on-the-fly space generation and that kind of stuff. Okay. I will not have time, but we integrate all these tools with, using Visio on one hand and using Eclipse on the other. And here we have some screenshots of the way we edit components, timing automaton. Okay, we write these kind of activity diagrams with timing information in it. We create the whole system under analysis as part of a project. We edit this VTS notation. Okay, here you see there are really few features to write down the scenarios. Okay, and we create the running example mixing system and analysis and properties to check. Well, and we feed the model checker. We get the counterexample, that kind of stuff that tools usually do with model checking. Okay, so it's a good time to stop. I don't know if you have any questions about it.
So I'm wondering, beginning you had this timed automaton, which basically are based on constraints for the model checking story. So do you have any problem with this symbolic state space exploration? I said deal with this by Uppsala or limitation of the approach, or would you benefit from having more powerful constraint resolution engines?
Well, for the timing automata verification, all this symbolic stuff must be there to make it decidable. If not, it won't work. There's some interesting topics about the way when you write down properties, one of the main features of timing automata is that there are some bounds such that if the clocks run beyond that bound, those values are not relevant anymore. So it's like, well, we know if X, there are some bounds which actually make it finite, the partition of the state space. Okay?
But it's real numbers anyway.
So
they are, yes.
Work with intervals.
They are real numbers, and there's a lot of work of making this as tight as possible, because here is really a problem. On the other hand, it would be interesting to have symbolic expressions in the guards. Okay, so saying like X is that a given C instead of a constant should be a symbolic a symbol. Okay, and something that would be really interesting is actually getting the constraints on C that make the property valid, for example. Okay, so this is some things were done, okay, on that direction, but still it's not something that you can get easily from current versions of the application.
Trial and error there.
Yeah, because this would be asking which is the C that make it.
The model checker was running 10 hours or so.
Yeah.
For this 48 or 38 nodes or something and 400 transitions or so. The question would be, is that actually related perhaps to this brute force trying out? And
the problem is the.
faster if you have
I haven't said that. Most of the work is symbolic here. Each node, the way this works is that for each location, you have plenty of symbolic representation of different regions of the state space. So, I mean, and this has a lot of to do with that, and also the number of clocks has an exponential influence on the model checker, because region has to do actually with n-dimensional spaces, and n is the number of clocks. So there's a lot of work trying to, building this tighter as possible. Things that we've done in OpSlice, which is saying, this clock is no longer relevant, so I can have, with less dimension, I can represent the state space, okay, that kind of stuff.
How long that 10 hours property, how long does it take after slicing and everything?
Well, that was after slicing. Without slicing, it just go out of memory, okay? But that was done with the old version of UPAL and not very modern computer. I think that example nowadays takes less than 2 hours, okay, without 2 hours, without, with upslicing. I think that 10 or more than 10 hours without slicing the model, okay?
Another question. So you're basically using linear arithmetics on timers. So I remember years back, I'm actually not so firm anymore with the real-time community, but for example, duration calculus, you probably heard about it. And actually, in this kind of modeling world, they're using also integrals and different differential quotients, so basically infinitesimal calculus on timing or so. Is this something which would also fit nicely here, or extension which you?
It would, but it is very easy to have a model which basic problems are not decidable. Changing a little bit.
Away for a second. From pure modeling perspective. So is this something you're missing when you're modeling?
Well, actually, timing duration calculus could be much more precise to express things about having a shared processor, because you can write things like, if you take into account a given interval, the time that the process spent in the processor accumulated should be less or equal than that time I wrote here, which is the execution time, okay? So you can actually build a more precise specification about the behavior of the system, and quite descriptive ones, okay, using things like duration calculus.
So
you can't do that. What?
So maybe not that much for properties, but for models? Is that what you're saying?
Yes, probably for models. Of course, there are some interesting properties that has to do. We're talking here more about hard real-time properties, but there are a lot of interesting properties about quality of service that has to do with behavior on the long run, okay, or probabilistic behavior, saying, this could eventually violate a deadline, but I mean, not too many times, okay? That's more or less the kind of things that we cannot easily express with this kind of formalism that would be interesting for the industry of what is called soft real-time system, okay? Where quality of service, it's really important, but it's really hard to describe and to reason about. So it's interesting because soft is harder than hard sometimes, and this is a case. you have to work with different tools, analytical tools. I mean, this kind of techniques aren't very suited for that kind of reasoning. This is more or less what I can say in a few words. I don't know if you have another question about it. It is interesting that this thing that is preemption, modeling the fact that processor maybe that maybe tasks may be preempted by other tasks. It's something that till 4 years ago was thought that could not be expressed and checked using timed automata. They check it using hybrid automata, which is more expressive and has non-decidable problems. But recently, they discovered that they can use timed automata or variation of timed automata to express and decide properties of a set of tasks that preempts between them. And the tool times is based on that theory. But the problem with the tool times is that it builds a kind of monolithical model. The thing that I said at the beginning of the talk is that, yes, you can do it, but you are modeling the scheduler. You can be quite flexible on the scheduler you are modeling, but it's very hard to localize properties. So you have a scalability problem there. So it's an interesting approach, but in practice you have to combine it with another thing because it's difficult to treat anything that, I mean, these kind of examples we tried and we get it out of memory very easily. So you have to tune it very well, and there is no warranty that would work for a larger example, actually. And so it's a kind of trade-off between, if you fix the application model, you can do some interesting things. Okay, analytical tools and conservative abstractions are there. If you're trying to be quite general, it's hard to get the most out of these tools. Okay? Thank you.